Right, hi, I'm Miro. Thank you for coming to my talk. You can see the slides. It's always something. Oh, okay, good. All right. So just please make sure that everyone can read all the text. These are like the smallest fonts that you're going to see. And so you saw me in the lightning talks, and I'm a professional at this. You may know me from previous. Why do you not switch? Oh, because I'm. You may know me from previous episodes, as you saw in the lightning talks. Angry Nerd Threatens ISO Committee, or How to Poison the Front Row Unnoticed. No front row today, although you are pretty far in the front, so maybe be careful. The title is the talk. We're going to look at these pieces on the left and see what happens on the right. The first thing, the three dots. This is for Variadic templates and parameter packs, and we are going to kind of blitz through these things because we want to see how it all comes together later. This pretty much allows you to have arbitrary number of template parameters on pretty much anything. Here it's on a type, here it's on a function, so you can also have arbitrary many function parameters. And you can then do the regular template stuff, right, at like const references or pointers, and each argument is deduced on its own, so they're independent from each other. You can then convert these, for example, here passing it on to a different type. So the capital A args, that's a type pack, and then the lowercase args is a value pack. At least that's my name for it. I'm not sure if that's official terminology. You can also modify these, right? You can, for example, strip all the references and the const volatile stuff from the types, or you can pass every single value through a function. So in this case, h is called once for every value in the pack. And note that the position of the dots is important because it expands the stuff in front of it on like the same syntax level. So this will call h once with all the arguments. This calls h for each argument. You can then have multiple packs in there. They just have to have the same length, otherwise it won't compile. So in this case, we call h with just each value added to itself. And then we can have nested expansion, where here we have also the pack twice, but we also have two levels of expansion. So you have to read it like outside in, right? So on the outside, we have the dots on the right, and it expands everything in front of it, up to the h. And then inside the h, we have the first args. That's actually the one that's expanded by the outer one. And then you have args again, and that's expanded on its own. So what we actually end up doing is calling h n times. First argument is that element in the pack, and the rest is all the arguments repeated. There's some cool stuff you can do here. We can put it on pretty much anything that's a template. So we have template aliases, lambdas, template variables, anything. Then in C++17 we got fold expression. It's a very powerful tool to actually use these, because up until now all you saw was transformations, right? One to one. Here we can do reductions. So for example, summing up all the values. The syntax for this is you have the dots, a binary operator, and an unexpanded pack, or an expression containing unexpanded packs. And this will do a left fold. It takes the leftmost values, combines them, that takes the result of that, combines it with the next, and munches left to right through the sequence. You can then switch it around and get a right fold that works through it the other way. So this is important if you need to control the associativity of your operations, or if these have side effects that have to happen in a certain order. Each of these also has a version where you can add an initializer element, which is basically just appended at the end or the beginning of the sequence, and then you do the same operation. You can use almost all operators. So the CP reference didn't list the spaceship operator. I don't know if that's real or just missing. It also doesn't have the scope operator, but maybe that's going to change with reflection, because then we can reflect over namespaces. Who knows? Note that we also have the pointer to member indirection operators. Can do some very clever things with that. And be careful with the comparison operators, because this does not do what you might think it does. It takes the first element, compares it to 0. That will give you a Boolean, and then we will compare that, recursively Booleans with every next element. So what you really want to do is do the comparisons individually and then make sure they're all true. What happens if our pack has these edge cases where it's either empty or only one element? The logical operations gives you the identity element, and the comma, if it's empty, gives you a void expression. And we're going to look at comma later because it's very cool. So if you need to be able to support an empty pack, make sure you use the bottom versions so you can compile with an empty pack. Otherwise, you know, the red cross, everything else just won't compile in that case. And one thing people often miss is that lambda expressions are expressions, which means you can fold over them. So this is pretty much the same as before, just written in a bit more verbose way. And note that this is an immediately invoked lambda expression. If you don't do this, you just get plus lambda, and it won't compile. Well, maybe it does if you're unlucky. So this is really cool. And you can have these packs anywhere in the lambda. It can be in the capture list, it can be in the parameter list, it can be in the function body, it can be in the call operator, the call expression, and it works, right? Anything. And we can do these fancy things with that. So in this case, we have a operation where I want to print all the pairs, all the combination of numbers I put in here. So with this output. And you can think of these fold expressions with the comma operator as like a for each loop, where every iteration is a different type, potentially. So with the outer loop, we iterate over the first sequence, and then for each of those, we iterate over the second sequence. And that gives us this output. Note that it's important that we have this capture here. If you do, right, see that? The inner lambda gets the capture of what is the value of I at this expansion, right? Because the compiler will just copy paste this lambda over and over and replace the IS expression with the current value. If you don't do this, then it won't compile because I and j don't have the same length. But also the inner fold consumes those two packs, and then the outer fold has no more packs to expand over. So it is important if you do nested folding to think about, you know, which fold consumes which pack and in which order. Yeah. And this is the C++ hates you pattern. You will see this over and over and over if you write code with packs, because there's so many algorithms where you need to associate a pack element with its index in the pack. And at the moment, there is no way to create a pack other than to inject it from outside. That means through a function parameter or through the template parameters of a class or function. So you will see this over and over and over and over in pack code. It just this annoying things about C++ that we don't have nice tools for. So just, you know, what happens here is you give it this make index sequence, which is a type that just will contain 0, 1, 2, 3, all the way to n-1. And then inside the body of the lambda, you now have access to two packs that have the same length. And you can expand each value of the pack with its index side by side. So this concludes the first. Any questions about that so far? Wonderful. So next, CTAD, class template argument deduction. This is really cool from Seguro 17, and it allows us to write code like this, which, if you know, vector has two template parameters, the value type and the allocator, and tuple has an arbitrary number of template parameters, and we don't have to specify them, because the compiler can deduce them from the initializing expression. So we get a vector of int, the allocator is the default value, and we get a tuple of int, double, and char. To do this yourself, it's very easy. You have a class with template parameters, and you have a constructor that uses all those template parameters. And then when the compiler sees this expression, it will look at your constructors, see which one matches. It will like pretend to call it, do argument deduction on that constructor, and if it can deduce all the parameters of the class, it will just put them in and then instantiate it. And with an aggregate in C++20, you don't need the constructor. It will work automatically, which means you can use designated initializers. This is pretty awesome. If you don't have an aggregate, you actually have constructors. You can also write deduction guides to control how this mechanism works. So let's say I construct foo with 1 and 2, but actually I want this to create an optional of integers. It doesn't have to be a template. You can also just put any parameters in. It's like you're basically writing an overload set, kind of. What you cannot do, unfortunately, is that you only specify partial parameters. You have to go all or nothing, which is a weird rule, because you can kind of cheat with an alias. So this compiles on all the compilers, but I actually don't know if the deduction happens or if int is fixed or not. So your mileage may vary. Then we have the next checkbox. So NTTP, we already heard about that from Ben earlier. And we had this for a very long time, right? So since C++98, we were always able to just have integer template parameters, which are values, not types. But it had to be that type. Couldn't use others. C++17, we can use the auto keyword here, and now you can use any integral type. Then we relaxed it in C++20, where you could also use floating point arguments and lambdas, because why not? And the big one, custom types. So this is now, at compile time, the value of a type you wrote that's part of the type signature. There are some restrictions on this where all the members have to be public transitively through all the base classes. You can't have virtual functions, you can't have virtual bases. It's a structural type, as it's called. And you can use it out of the box with many types in the standard library, like std array, for example, works. Pair also works. Tuple, unfortunately, doesn't because it doesn't have public members. And that's a big constraint, unfortunately. You have to be careful, though, because the compiler, if your type has an equals operator, the compiler won't use it. So these types are defined as have structural equality. That means the compiler will go through the member fields and compare them for equality. So if you have your own equals operator in there, make sure it's doing the same thing. Because otherwise, your code will behave differently in the type system versus at runtime. So that's be careful about that. And here is something to be aware of. There are some traps, of course, because it's C++. It'd be too easy otherwise. Note that this doesn't say C++23. It's C23. So this is a feature that just came into C. And it's like an include, except it takes the content of the file and puts it basically as an array of numbers into your code. And it's pretty cool. But it also means you can have now very large data sets in your compiler. The compilers are smart about this. They're going to do like memory mapping and some stuff like that, so not actually load this like in some internal representation. But because C++ is value-based, when you take this variable and you stuff it into the signature of a type, you'll get a copy. And if this array is a few hundred megabytes, that's now where your compile times tank, and you may crash the compiler. You can fix that by using a reference parameter. So this won't make a copy. It's like if this was a function with a reference. Or you can use decotype auto, which, just like decotype auto for function return types, where you can either return by L value, R value, or copy, which is deduced from the expression used to initialize this. But now we need to put these parentheses around the variable, because an object itself is not an expression. And when you put the parentheses around this, you now turned it into an expression. And so now it's an L value. So probably not what you want to do, because now every time you have to use this foo class and you want to overload on it or specialize, you now have to be aware of, is this a reference or not, and it's just kind of annoying. So it's better to have a dedicated type where you actually, that's only using the references. Most of the time you won't really have to worry about this, but if you are in that camp of people who like to have gigabytes of data in the compiler, looking at you, you may you have to be aware of this. And this also happens when you copy or when you copy a value from one type to another, right? Because the value is part of the type signature. So foo of x is different from bar of x, and the compiler will make a copy of this variable, and it will even involve copy constructors if there are any. So again, usually not something you need to worry about, but you should know it if your compile time suddenly start tanking and you didn't just change some array size somewhere. Then this is something that really annoys me, but these variables, these NTTPs, they exist as objects in your source code, right? They exist as constants somewhere. And you can get a reference to them for comparison or for using them to somehow access data, make compile time decisions. So when you do this and you pass it in a standard array with 3 elements, you will actually get a reference to that variable that exists somewhere at compile time. When you do the same with an integer, it won't compile. It says returning reference local temporary. This is so annoying, because what happens is, if the type of the variable is a built-in, or a C array, it will always materialize as a temporary, which is really weird. I don't know why. So again, we have the same problem as before. We use deco type auto, but this time it's a return type. So this looks more like a regular meta function you could write. We use the parentheses, and now it works in both cases. So these are some of the traps to be aware of. So this concludes the prequel. Any questions before we continue? Okay. So we actually have to. Why is my mouse moving? Stop that. We will apply this to a real-world application and see the problem that we have and then how we solve it. And I really would like this to stop moving. Okay. And the domain we're going to use is thermodynamic simulation. And in a thermodynamic simulation system, you have models, right? Like models like you maybe had in school to calculate the volume of an ideal gas. But models also you probably didn't have at school, like DIPA 105, which is to calculate the density of a liquid. Or Lee, which computes the heat capacity of an ideal gas. And many, many more. I mean, there are so many. And you notice that the one on the left, it looks like a pretty classical physics equation, right? You have temperature, amount of substance, pressure. Those are quantities that we can kind of deal with, right? I think each of you can kind of imagine what that means. But then we have parameter, 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 parameter. What's up with that? So these are called parametric models, which require you to fill in the parameters. And so what companies or scientists do is they reproduce something in the lab and they take measurements. And then they fit these parameters so that this function reproduces the measurements. And this is the secret sauce of these companies, right? These numbers are worth millions because it's very expensive to get them. And this isn't the end of it, right? So many physical equations are like a pipe. You need to compute one thing, then you can compute the next thing, right? You cannot compute the volume if you don't know the pressure of the system. And so you put them in graphs, where on the left you insert something like temperature, pressure, composition. In this example, we're going to use the composition of air. And then for every component, you have to calculate these properties up there, the viscosity of that component, the saturation pressure of that component, then the viscosity of that component from that, and then you combine them together into a liquid of the viscosity of the liquid as a whole, right? And I say liquid here because when you take air and you cool it down far enough and you put it under enough pressure, it turns into a liquid. And so this is important for like air separation, for extracting nitrogen out of air, for example. And this is just a tiny little sliver of a real-world system. In a real production configuration, you could have hundreds of models with thousands of parameters. And so nobody wants to write these by hand, right? You need a tool that configures them for you, then you load this configuration file, you set up your models, how you need to connect them, and then perform the calculations. So the first motivation for this is to take the source code of C++, which is the ground truth of how the models are implemented, and export some kind of description of that, which you can then import in the tool that creates the configuration. So for example, that can also then support the scientist to say, hey, this thing is a temperature, you try to put it in as a pressure, that's not gonna work. And to do this, you're gonna need a little helper, which is not really much of a helper, it kind of carries the entire thing. Right? This is the most important data structure we're going to use. It is my version of a tuple, but all the values are in the parameters of the template. Right? So this thing is empty at runtime. It doesn't exist, basically. We give you some helper functions, like the size or index sequence, which, as you saw before, it comes up a lot. So this is a nice little helper. We implement the std tuple interface with the get function, and an equality operator that just returns true if the two parameter packs are equal, which is useful to have for testing mostly. And now with this, we'll basically show you the solution to the problem, and then we're gonna go looking at how the solution actually is implemented. So this is what we're going to create. It describes all the inputs and outputs of the ideal gas volume function. We have a temperature and a pressure and composition as input, and we have volume as output. And we define all these things in here. We define, is this an input or output? What is the physical dimension of this argument? What's its input and output domain? Which values are allowed to go in? So most of these are not negative because we are in Kelvin, so negative temperatures don't exist. Negative pressure doesn't exist. Negative volume doesn't exist, and so on. And we also have extent constraints. So many models don't just work on scalar numbers, they also have inputs, vectors, like here in composition, or matrices, or high-order tensors. So we can also say, the inputs must have certain constraints on the sizes. An example for that is a matrix multiplication, right? Where we have the constraint that the inner dimensions of the operands have to have the same size. And the output of that operand has the size, the outer sizes of the two inputs. And this is how we can express that. We say the inner dimensions of those two inputs must be the same, and the output dimensions of these also have to be the same. And we can also use constants, because some models do that. They just say the first input just has 2 rows, because that's how the equation works. And so the way we're going to build this up is by having this first class, which is like the outer container for each argument. The name and descriptions, the fixed strings, I won't go into those. You can Google that. It's just, you have to get around the fact that you cannot use string literals as template parameters, and this is one way to do it. You can find plenty of implementations online, and it's also proposed with a standard. So you're going to ignore those. And we're left up with the 4 fields that are kind of interesting for what we actually want to do. So we have the flow, which tells me if it's an input or output. And we also have as a reference the actual installation here. So the flow. I choose to just go with separate types. You could also use an enumeration. But I think types are better here, because if you want to add a different type of flow, like it's a temporary or something, or a discarded output, then you have to modify the enum. This way you just add a new type. You add new overloads to your existing functions. So it's better adhering to the open-close principle. So when we do this, the flow member is going to have as type input t, and that's what then goes into the first template parameter up there. The pressure, we are going to ignore the physical dimension here, because that's something from the MP units library by Mateusz Pusch, which basically is doing the same thing as here, but it is such a huge topic that we're not going to go into that. The domain is also not very difficult. We have this domain on 0 is actually a variable that is predefined by the scientists, because it's something they just use over and over and over. And you see that it is an instance of domain. Domain is an instance of a type called domain t. I will show later why we're going this proxy through the variable. A domain is just an interval or a collection of intervals, and we derive from tuple, so you get access to all these nice member functions. And because every domain is also a tuple, but not every tuple is a domain. And an interval is just a lower bound and an upper bound, and then we have an inclusive bound and an exclusive bound, again as separate types. And so now the reason that we use a variable instead of a type is that if we use the type, we would have to do this boilerplate nonsense up here. I just hate that, right? I want it to be nice and concise, so by using the variable, we can get rid of that. Then we have the actual container for everything, right? We have, again, just I'm too fast. The extents constraints are similar, but there's much more freedom here. We could also add concepts and stuff like that, but I didn't really want to, because it'd just be too much. But you can also do that, and this is pretty much the same concept as before. We have a variable of a type, so that we don't have to do this curly braces stuff, boilerplate. And I want this to have as little boilerplate as possible, because the target audience are scientists. They are not C++ masochists like us. They just want to get their job done. And the constraints are also just empty types. They're just tags, pretty much. There's no information in them other than their identity. Then we put all of this into one big tuple that gives us access to this nesting here. And that's how we end up here. Any questions so far? All right. Then I think it's time for some code. We have the this file, we have the definition of the classes. Let me know if it's too small. If you need, shall I make it bigger? Yes, okay. Better or more? Okay. So what I didn't show on the slides is that because these are just variables, you can also declare them separately. And because like temperature, as you saw, was used by 3 or 4 models, and it shows up again and again, again, again. So many models have temperature as input. So we can do simple normal C++, we just reduce that value. Just put it in there. Works same for pressure and decomposition. And then the output is special, so we put in there directly. And I have a bunch of models here. So DIPA 101 is for viscosity calculations. We have to sum up 2 vectors. What we see here that there's a constraint on all 3 parameters because all the 3 vectors have to have the same size. And we have the definition of the matrix multiplication with the constraints of the 3 constraints that we care about. Right, so this is the definition of the model interfaces. And then we just have to put them all together into one place. So I create an enum for every model because we do need to kind of decide at runtime which model to execute. So we do need a runtime value. And we do the same trick as before. We create a type that has the type of something else in it. And we can use CTAD down here to just create a bunch of these. And the model catalog, again, is a tuple. So every entry on the tuple can have a different type. And that's how we can put them all in such a nice list. So remember, the original motivation was to export this to some data file. So we're going to just do very simple JSON here. And you will notice that it's actually not that interesting. I think it's pretty boring, which is why we're going to do other things. But you see the pattern here is a fold over a lambda. And then it's a for each loop, basically. So the body of the lambda is just stamped out for each type in that tuple. And then we go up to serialize the individual parameters. It's again a fold over a lambda. And we have other things here like the constraints, a fold over a lambda, right? You get the picture. You're basically just writing for loops, except that each iteration of the loop can have a different type. And so all this is dispatched at compile time. And we can then run this and see that it hopefully creates the JSON file. That blue color is really hard to read. Maybe I should. Ah, yeah, that is bad. It's more black than green. But anyway, yeah, so we see the JSON is here. We don't really need to look at everything, but the stuff is here. So this is now, I can have the ground truth of my C++ application, dump this JSON file on every commit or something or release, load it into the configuration tool, and then it has the actual representation of the implementation in the actual tool that does the calculations. So this is the first one. We're also going to look at those domains because I also want to write or use this inside the actual application, not just to export a file. So I want to write a function which I can give a value and this domain thing, and it tells me if the value is in the domain. So we have the implementation of the domain stuff. Why aren't you switching? Sorry that you can my beard scratching. I'm just too manly for this microphone, I guess. Okay. The implementation is also not really difficult, right? I think you would also write this kind of code mostly if it didn't involve templates. We have 4 functions to compare the lower and upper bound, each with an overload of an inclusive and exclusive bound. This is just basic comparison of floats. We also have some special handling for NINs because sometimes in these systems you use NIN as a special marker value that something doesn't exist so that you don't need to reallocate memory for it and so on. So we have these 4 pretty simple functions form an overload set, and then here's how they're used. I can have a function is a value in an interval, which then just compares it with the lower and upper bound. Can ask, is a value in the domain, which then just folds over all the intervals. It has to be in at least one of them. And I can test an entire range of values if it's in the domain, which does the call in each of them. And this is all folded at compile time, inlined fully. So there's pretty much zero overhead here. Not pretty much, it is zero overhead. And we have a bunch of tests down here. You will later get a link to all the code so you can look at it yourself. There's pretty extensive, going through all the edge cases. So it's all here, right? So I think it's pretty cool because now you can, with a very little code, and you can see it's like less than 50 lines of code, you can create a system that you can throw any kind of interval or domain definition at, and it will do the right thing. So you can have domains with only one interval, accept everything, accept only positive numbers, only negative numbers, or in this other case we had, because we're using something for division, accept everything except 0. And you can build up these intervals to do all these comparisons. It works just fine. Do you have any questions about how this works so far? Okay. Very good. Now, off to the slides again. And now we're going to look at the extents implementation. So this is also something I want to test. This time we're going to have a look at how it actually works in the algorithm that we're going to use. Because there are multiple ways to do this, and this is the one we are going to use because it's pretty easy to implement. So the matrix multiplications, we have two inputs, one output, and in total 3 constraints. And we start by extracting all the unique constraints because they're just markers, right? And we just know that all the dimensions that have the same marker have to have the same size. So we take these 3 types and we wrap them in a special type called a constraint size, which associates each constraint with a number. And we start with -1, which means we don't yet know what the constraint has to be. You plop them in a tuple, and now we have state, runtime state, in this table here. Now, as a reminder, this is how they're defined for the 3 parameters. And we're going to feed these 3 matrices in as function arguments. So these are the size, right? On the left is the rows, on the right is the columns. And we're going to iterate through the constraints. So we basically take the constraints and concatenate them all into one big list, which would then have 6 elements. And we go through this and say, okay, I have this constraint here. Let me look in my table what the value is. Okay, it's -1, which means this is the value that it has to be. We set it to 3. Then we go on to the next one. Again, the value is -1. We don't yet know what it's going to be. We set it to 5 and move on. And now we see the constraint again. We look at our table and see, oh, it's not -1, it's 5. So this matrix now has to have 5 rows, which it does. So we're good. We go to the columns of B, and we do the thing again. It has only 2 values. So -1, I mean, and then it assigns the number of columns to 2. And then we just repeat this for the others and make sure that it's all the same. And they are, so it works. If we do not have the same number, so if we're at this point where we're comparing the second time inner shows up, we see that it's 6, but it's supposed to be 5. So we reject it. So this is how it works. It's not the most efficient way to do it, but it's the easiest to implement. So that's why I'm going to show it. Ideally, you want to create code that doesn't need this temple, that just directly stamps out, compare this value with this value, this value with this value, and this value and this value, right? Maybe I'll add this to the code I'll show later, but I don't have it in there right now. And so, how do we implement this? Right. Oh, this is terrible color. Much better. Okay, we have the extents calculation here. So this time we start at the bottom. We have this entry function here that we will call with the extents. So I'm not actually using mdspan for 2 reasons. One, the compilers don't have it implemented yet, not everywhere. Yeah, finger signs getting it. One problem for us, at least, with mdspan is that the number of dimensions is fixed at compile time. But we have a dynamically configured system, so this is not the case. So we're going to use a very simple replacement, which is this empty span structure, which contains an array of the size of each dimension and a count how many dimensions does it actually have. And so what we do in our check function here, we give it the list of extents. So these are the extents of all the inputs to the function and the outputs, right? Because we don't want to copy data around, so the outputs are also passed basically by pointer, so to speak. And the tuple of the descriptors. And just a reminder that this tuple class is empty, right? It has no state. So the ABI will probably also just remove it from the call. It just doesn't exist at runtime, pretty much, until you take its address. The next step, we go a level down, is we make sure that we have the right number of inputs and outputs, because again, it is a dynamically configured system, but you have to match it against a static thing. And we then also check that every span has the right number of dimensions. So if we have a tensor or matrix or vector or more. And down here we then see the things we did on the slides, where we extract all the unique constraints using some algorithms that you can also find in the code later. We concatenate all the constraints, and then we remove the duplicates. The constraint sizes is the tuple. Yeah, that's making the tuple. So it's not very difficult either. It's just make tuple, right? And then we do this fold. We can't use a loop because each constraint has a different type. So we have to fold, but the spans go in as a span of spans, span of span extents. Right? It's an array, basically. So we use an iterator to go for each expansion of this fold. We just increment the iterator so that match each constraint, which is a compile time thing, against the runtime value that's in the iterator. Further, we go another level down, where we now check a single extent against its constraints. And here you see the pattern I showed at the beginning, where we actually now need to match each constraint in my definition against the index that belongs to it in the extents. So the first dimension, the second dimension, the third dimension. So this is where I need to pair up each member of the pack in the tuple against a dynamic runtime value. Well, it's not dynamic, but it's a runtime value which I use to index the extents. I again call check extent now on each dimension, and they all have to match. And so here we see access to the std get to the tuple, and we're using the version of it that doesn't take a number but a type. And because we know that all the types in the tuple is unique, this works. And the constraint size is actually a little bit bigger than what I showed on the slide, because we have these the size, which is the -1 constant at the top there, and we just have this function to please check yourself against this value. And so here is the logic of the -1 handling. If it's -1, set it and accept it, otherwise check that it's the same. Then we have a specialization for integral dimensions, where we don't need this -1 or any kind of checking, right? It just has to be 5. If it's not 5, it's wrong. And we have a special tag, unconstrained, which just accepts anything. And we can again see down here a bunch of tests. So we have the replication of the matrix multiply here only with constraint tags. Then we have one that only has numerical tags of constraints, and one that mixes them. And then again a bunch of tests. These are the happy paths, and then a bunch of unhappy paths. Make sure that it actually does what it's supposed to. You can again run it, but it's actually the same code. It hasn't changed, so you already see that all the tests passed. All right. Any questions about how this works? Yes? Please wait for Mike.
I think you seem to be doing a very great job in abstraction, but my question here is, why don't you use Haskell or Rust for such type of problems?
Because we need the performance of C++.
But don't you have the same comparable performance of Rust, but extended type system?
I mean, then it wouldn't be a C++ talk.
I see.
No, but
Legit.
we don't use Rust because we have other requirements that Rust doesn't fulfill for us. So there are certain types of libraries that we need for the simulation stuff, and they don't exist in Rust. Which actually is the only reason why it's done in C++. Any other question? Okay. So then, we go to the result, and I think I need new glasses. So I think this is pretty cool. I mean, this is only scratching the surface of what you can do, right? It allows, I think, is like almost no boilerplate. There are things about this I don't like. I don't like the fact that I have the angle brackets, the scare brackets at the beginning and end. Also around the constraints object and so on. I wish I didn't need them, but I currently don't think that there is a way to do it without them. Like ideally, I would like things like member packs, where you could just have curly braces everywhere, because that's what everyone's using for this kind of stuff. Like in every other language, right? You just have arrays of objects and so on. That we're not there yet. Maybe C++ will add these things in the future. But until then, I don't know how else to do this. I was also giving this at my local meetup, and I discussed this for like an hour with someone, but none of the ideas we came up with worked. So if you have an idea how this could be done without the square brackets, scary brackets, I mean, then let me know. You may have guessed that those were not the real titles of my talks. So these are what they're actually called. You can find them on YouTube if you want. And ta-da! This is the Compiler Explorer link that has everything implemented. I showed you literally everything. The only thing you may need to know about it is that because I'm using a bunch of libraries, it doesn't always finish compiling. You can run into the timeouts. So just open the CMake list and comment these CPP files in and out to make it compile, or run it on your local instance, however you want. But it does everything I showed, compiles and runs on Compiler Explorer with Clang 18. It also works with GCC 14. It also works for Microsoft. That's what I did on my machine. But Compiler Explorer doesn't have library support for that, so you can't use it there. GCC only works if you remove the units library, because it can compile it apparently yet. But then everything I showed works when you remove that. So that's it. Thank you very much. And if you have any more questions.
Have you tried with modules? Oh, I got a glass. How with the glasses. Did you try with modules?
I did not, no. But there is nothing that should prevent modules.
No, it wouldn't change anything.
Yeah. Anyone else? Wow, satisfied customers. That's great. Oh, now there's one, of course.
Yeah. So I also maintain some kind of a database, code base. How many people are able to understand this level of abstraction and be fluent in extending it?
I mean, I would argue, when you look at the code, that if you look at the domain example, right, it's 50 lines of code to implement this, right? And it's not complicated. It is template metaprogramming, right? So it's scary, but it's not the type of metaprogramming people are usually scared of, right? It looks like normal functions. You have some templates there, you have the fold expansions, but I think these things are pretty easy to understand. They're not that complicated. And I don't think you need a huge team of C++ nerds to understand this. And yeah, this is code that would be implemented by the software engineers and then used by the scientists to do this stuff, right? So this is the different audience, because this is a project that has software engineers and scientists working on the same code base. The scientists only write their physical models and the stuff they care about. They don't mess with all of this. That's why the team also has C++ engineers.
Hi, Alex here. I apologize, I missed the first few minutes of the talk, so if you said it already, I apologize. During the first part of the talk, you mentioned multiple times like compiler error, compiler wouldn't build it, stuff like this. Is there anything that compiler dependent, or it's like it will be the same behavior across all of the compilers? It's actually standard.
The behavior is the same, but the error messages are very different. Like, some compilers are better at this than others. Microsoft. Like, I have to say that the Microsoft compiler is really not great at error messages. It often just kind of fallovers and says you constraint not satisfied, and that's it. Right? So yeah, we could go into how to design it also to make the error messages as easy as possible to understand. You know, we also had a lightning talk about where someone tried this and failed. So this is definitely something that's difficult. Like, I know that Eric Niebuhr put a ton of effort to make compile errors in his ranges library as understandable and as short as possible. You have to put dedicated effort into making good error messages in your template code. I know that there are some proposals where, for example, they would let you emit a custom error message from a concept if something is not satisfied. So there are tools coming to the language to make these things easier, but you know, committee is slow and things take time. Anybody else? All right, everyone's happy. So thank you again for coming and enjoy the rest of the conference.